So hello everyone, and today we are going to do the third session on the FloEFD training. So my name is Ajit Singh, and let's get started. So the objective of today's session is to check and do the comparison between the use of two different porous medium and a catalytic converter, and the type of analysis is internal. So in the last example of wall, we saw that how we can check the wall resistance or pressure drop because of existing model resistance. This learning will help us in our today's session, where we do have to select between two versions of catalytic converter. In this tutorial, we will consider flow in a section of automobile exhaust pipe whose exhaust flow is resisted by two porous bodies serving as a catalyst for transforming harmful carbon monoxide into carbon dioxide. When designing an automobile catalytic converter, the engineer faced a compromise between minimizing the catalyst resistance to the exhaust flow while maximizing the catalyst internal surface area and duration that the exhaust gas are in contact with the surface area. Therefore, a more uniform distribution of the exhaust mass flow rate over the catalyst cross section favors its serviceability. The porous media capability of FloEFD are used to simulate each catalyst, which allow you to model the volume that the catalyst occupies as a distributed resistance instead of discretely modeling all the individual passage within the catalyst, which would be impractical or even impossible. Here, as FloEFD tutorial example, we consider the influence of the catalyst porous medium permeability type, which is isotropic and unidirectional medium of the same resistance to flow, on the exhaust mass flow rate distribution over the catalyst cross section, and we will observe the later through the behavior of the exhaust gas flow trajectories distributed uniformly over the model's inlet and passing through the porous catalyst. Additionally, by coloring the flow trajectories by the flow velocity, the exhaust gas residence time in the porous catalyst can be estimated, which is also important for the catalyst effectiveness viewpoint. So let's get started. So this is the model which we have currently in our hand. I have created a section view which will facilitate us to access the other faces where we have to apply the boundary condition. So let's get started with the wizard. So we can make it porous medium analysis. Let's click on next. We have the unit system. We can change any unit and we can save, but right now it is okay. This is the internal analysis, and yes, I'm going to take air. You can take even carbon monoxide or carbon dioxide here. So we are not seeing the chemical reaction. We just want to see how much time the air or fluid is going to be into the system and how uniformly it is going to distribute throughout the porous medium. So I think air is a better medium to work on for right now. And let's click on finish, and we have this computation domain. Let's hide this computation domain. Now let's apply the boundary condition. In the boundary condition, we have multiple options like inlet mass flow, inlet mass flux, inlet volume flow, or inlet velocity. So I'm aware of the inlet velocity in this case, which is 10 meter per second, and it is going to in from this area, right? And you can click on OK. You can add more properties like turbulence parameter or boundary layer information, but this much is enough for right now. Okay, now let's move on to the other property, that is how it is open to the other end. So this is having the opening to environment with the static pressure of environmental pressure. So I'm going to click on OK on this. So after the application of boundary condition, we have to apply the porous media. Okay, so here we have porous media with us. You can go to condition and you'll see it here. You can add any component in the tree also, like you just have to right click on the project and click on customize tree, and you'll get all the other options which you can add in your simulation tree. Okay, so here you have porous media option. You can click on inside porous media, select those components. We have multiple predefined material. You can check, right? Or you can create your own material. So you can go to the engineering database where you can create your user defined material. You can take use of existing material by copying it, and you can go to user defined and you can paste it here, and you can edit the item properties. So in the porous media, the important information which you have to provide is mass flow rate versus pressure difference curve. So that means how much mass is passing through by applying the pressure in a porous media. And you can also define the porosity here. So we are using 0.5 porosity, which means 50% of the medium is empty. So parallelly, you can also change the behavior of the material, like you can make it isotropic, unidirectional, axisymmetric, that means for the cylindrical objects, or orthotropic. So that is the way you can change the behavior of any porous media. Okay, so let's close this and cancel it, and let's go with the predefined one. So I'm using the isotropic material right now. Let's click on OK. Let's create the goals here first. So we can go to insert surface goal. You can click on these faces. Okay, and you can click on these two faces very easily, and you can create goal for individual faces by clicking create goal for each surface, and you can make average total pressure. You can click on OK, and it is done. So you can cross verify the sequence. This is your outlet, this is your inlet. You can create one more equation goal. So it is very easy. You just have to select the goals which you have already defined, and you can create the equation and expression. Okay, so that means okay, apply the minus sign. Apply the minus sign. So this is inlet minus outlet. Click on OK. Now we have all the things in line. We can go to meshing, and we can click on setting of initial mesh, which is I think 4 is enough, and we can click on OK, and we can click on run, and a new calculation will start. So you can check the solver window. And you can even clone it, and you can change the properties by selecting the parameter from pressure to velocity, and you can see the effect of this porous media into the system. Okay, so here the system is offering 12 point something meter per second of velocity, and we can also check the equation goal. Here we can see the pressure drop is around 119.646. Okay, so solver is done in solving the CFD problem. Now we have to see the results. We can see through the cut plot. Okay, and I'm going to apply velocity here with vector. So like that, we can see the velocity profiles, which is more practical to see, right? We can see how these velocity vectors are behaving. They are going like they are coming from here and they are not taking any sharp or sharp turns. But after some times you can see it is becoming very laminar kind of flow. So this is the example with the isotropic material. We have already made a unidirectional fluid flow example in which we have done the simulation and we have the results plus, and you can check the flow trajectories. You can click on show. So you will see the flow trajectory here is a bit disturbed in the transition between the first porous medium to second porous medium. Okay, whereas in the case of isotropic, you will see a more consistent flow, like there is no sudden change in the velocity. So this is more uniform flow in the isotropic. We can also do the comparison of the visualization, but instead of doing the comparison between this, let's do the comparison between this plot. Okay, which will give more information. So here you can see this blue region, the light blue region is more consistent and uniform. And let's do the comparison. So we have this compare tool which will help you out in doing the comparison. So we can do the comparison in all these studies or the selected studies. So I can go to this plot and I want to see the comparison between these two studies on this plot. So when I click on compare, it will create the comparison. You can check the plot. So in this example, you see, let me hide the things. So in this example, you can see here this in the isotropic, the fluid flow is more consistent. Here it is not so much consistent. So unidirectional is not a good choice from the product performance point of view, as well as from the cost point of view, because unidirectional porous media will be more costly than isotropic media. Okay, so this is a very nice tool to interpret the results between the two different studies. Okay, now we have this plot called goal plot, and we can check the goal plot how it is behaving. So let's see the goal plot in these two studies. So let's go to edit definition and click on show. So in the equation goal we can see 121.53. so that is a drop in the isotropic, whereas if we see the same thing in unidirectional, so it is 118. So here the pressure drop is the pressure drop is less in the unidirection, but it is not so much consistent in its behavior. So we will go for the isotropic porous media. So this is the kind of trade-off which we do. Okay, and the best part is with the help of fluid flow, that is inlet velocity, you get the pressure at this phase also. So it will help you out to get the pressure values to feed in by the engine system, or you can say the motor and pumps and system. So that is a very nice thing. So to get the rating, this kind of analysis will give you better answers, right? Because of resistance, how much pressure you need to apply to push the fluid out the system. Okay, so thank you for listening and have a great day.